to look at is radicals. So last year we looked at radicals, but we didn't really look at radical graphs. We looked at operations as radicals. So we added radicals, subtracted radicals, multiplied radicals, divided radicals, solved double radicals, so many things. Okay, we're going to go, our lessons that we learned this year are, we look at radical graphs and transformations and have to come up with equations. The second lesson we learned, but we're going to learn it last, is I give you any function and I ask you what's the radical of that function. So the entire function's under a radical sign, what happens. And then the third lesson we do, which we're doing tomorrow, which is out of order, we're doing solving radicals. So we did solving radicals last year. It's just kind of a repeat of last year's solving radicals, but we don't have double radicals, which is nice. You can't have two, so it's actually easier. And that's going to be the radical unit. That's it. Okay. So we're going to start off with the graphs. So we're going to look at the very first graph, and we're going to look at all four of these graphs, and we're going to draw them based on our base function. So the base function of a radical graph, if it hasn't had any transformations, is actually the y equals square root x graph. Okay? If I went to go draw it, I could make myself a t-table. If I plugged in -1, what would happen for x? Square root of -1? Not happening. I'm just going to say no. That's what your calculator's thinking. Nope, not happening. So we know that when we have square root functions or anything with an index that's a... Were you gone when I handed them out? Maybe that's not. When we take the square root of anything, we can't take the square root of a negative. We can take the cube root of a negative. So any even index, which is what it says at the very top of your paper, anything that has a restricted, and it should say domain, not remains. So cross out the word remains, which is weird, and I don't even know what happened there. Cross that out and write domain. So it says radical functions have restricted domains if the index of the radical is an even number. And for this case of grade 12, for this unit, everything is just square roots. So we're going to have restricted domains for all of them because we can't have negatives. So our restricted domain for this one would be x has to be greater than or equal to 0. We agree? That's what we're coming up with out of this t-table. Can't have negatives. So our first number, our first x we can have is 0. Now the square root of 0 is 0. So we have a dot at 0, 0. Then our next one we're going to do is 1. And then what's the square root of 1? 1. So our next point is at 1, 1. Should be a curve, not a straight line. And then I'm not going to do 2 or 3. Could I do 2 and 3? Yes, they just be decimals and I'm lazy. So I'm going to do 4. What's the square root of 4? 2. And then what would be the next one that I maybe want to do because it's nice? 9, which is 3. And then you connect all your dots. This is going to bother me. I have to redo this. Then you have yourself a radical. And our radical graph only starts at x is greater than 0. Now some people say, but we need the other part of the radical. No. The only time you get a plus or minus sign in front of a radical is if you take the square root of something, physically yourself. It was x squared equals something, and you take the square root of it, then you put a plus or minus sign in front, correct? Did you take the square root of this? No, it was there. So it's just positive. You can't just be like, oh, they must have forgot the plus or minus sign. I will help them out. No, you cannot, okay? They didn't forget it. This is what it is. All right. So that's our original function. Now we're going to use transformations to our original function to draw the next 3. So what's happening here? What transformation? Horizontal translation 2 to the right. So we could use mapping, and we could go x plus 2 comma y and apply it to our 4 big points, 0, 1, 4, and 9, right? We could. Or because it's just literally one transformation 2 to the right, I'm literally just going to move the points 2 to the right and redraw them. So it's now going to be at 2, 0, 3, 0, or sorry, 3, 1, and 6, 2, and 11, 3. And my graph moves to the right, sorry. What do I have to do with C? What's the very first thing I need to do with the equation? Take out the -1. So we technically have a vertical stretch by a factor of 3, a reflection in the y-axis, and a horizontal translation 1 to the right. But what's the easiest way to move points? What did I teach you? What's the mapping? Mapping is the easiest way. Anything under the radical affects the x. So my mapping now is going to be xy becomes, I'm going to negate my x's, so negative x plus 1. And what's going to happen to my y's? Anything on the outside of the radical affects the y's, so what's going to happen to my y's? Multiplied by 3. And I just apply it to my points, 0, 0, 1, 1. Four, 2, 9, 3. So 0, 0 is going to become negative 0 plus 1, 3 times 0. So it's 1, 0. What's the only thing that affected my original point, that original starting point? What's the only transformation that affected it? Just the translations. Now, why don't our reflections or stretches affect that original point, the 0, 0 point? Reflections and stretches do what operation? What mathematical operation? Multiplication. When you multiply anything by 0, what happens? It's 0. So the only thing that's actually going to move this 0, 0 coordinate is transformations. The translations, sorry, like the horizontal and vertical translations. So the great thing about radicals, and only radicals, is that by looking at where you start, you instantly get the translations. No other equation does that. Only radicals, because we start at 0, 0. Okay. So we now have 1, 0. Then we plug in 1, 1. So we're going to get negative 1 plus 1, 3 times 1. And we get 0, 3. Wait a second. It's now going left. Why is it going left? It was going up and right. Now it's going up and left. Reflection in the y-axis. So it caused it to go the other way. This one is going to be negative 4 plus 1 and 3 times 2. So it's going to be negative 3 and 6. And then this one's going to be negative 9 plus 1 and then 3 times 3. So negative 8 and 9. And you always put an arrow on the end because it keeps going, right? I want you guys to do D. My hint to you is, do I label any of these spots? No. So really on every single one of these graphs, I should be writing X scale. Oops, that is a C. X scale 1. That means every tick is 1. And I should be writing Y scale 1. Because we're just assuming they know that those are 1s. But is that okay to do that, to just assume? No. So I'm going to give you a hint. This one here, in order for you want to try and fit as many points as you can. The Y scale is okay at 1, but I would make my X scale be at least 2. You could make it be 3 or 4 too. It's up to you. So try and do this one with mapping. So this graph, we have to take the half out. When you divide by half, it's like multiplying by 2. My mapping is going to be xy becomes 2x plus 8, because it's a horizontal stretch by a factor of 2 and you're moving 8 to the right, bracket negative 2y plus 3. So I'm going to get 0, 0 is going to become 8 and 3. Why do I know that immediately? Right. The other two, the stretch and the reflections, when I multiply by 0, they go away. So the only thing on a radical, which makes a radical super radical, is that the translations only move in. So we have 8 and 3, 2, 4, 6, 8, 1, 2, 3. Okay. Then we have 1, 1, and it becomes 2 times 1 plus 8, negative 2 times 1 plus 3. So I'm going to get 10 and 1. Is that true? Oh my goodness, yep. Oh, 2, 4, 6, 8, 10, and 1. And then I get 4, 2, which becomes 2 times 4 plus 8, comma negative 2 times 2 plus 3. So I get 16 and negative 1. 2, 4, 6, 8, 10, 12, 14, 16, and negative 1. And then your other one's too big, but what does it become? What does 9 and 3 become? Anyone? Bueller? Bueller? Did you really not do this? Yeah. Yeah. My chart goes to 24. So technically, or I think goes to 16, 18, 20, 22. So it'd be like here. Okay. Let's quickly go through and do the domain and range. The domain of this one is from 0 square bracket, because it's inclusive, to positive infinity. And my range is from 0 to positive infinity. Or x is greater than or equal to 0 in set notation, with the squigglies and the x's and the xers at the end. It's more squigglies. That's set notation. This one, my domain is from, close bracket, 2 to infinity. And my range is from 0 to positive infinity. So it's low to high. This one, my domain is from negative infinity to 1, low to high. You can't go 1 to negative infinity. That makes no sense. Range is from 0 to infinity. And then this one, my domain is, oops, I'm not doing set notation. My domain is from 8 to infinity. Remember that you made your scale be 2, because some of you guys will say 4. And your range is less than 3, so from negative infinity to 3. The only x-intercept I'm going to do is the last one, just to prove a point. If I ask you for x-intercepts, and we're going to do this in more detail tomorrow, I need to fill in y equals 0 and solve for x. We agree? So it's going to be 0 equals, please tell me what it equals. 0 equals negative 2 square root a half x minus plus 3. Thank you. So we have to isolate for x. So the first thing we're going to do is what? Subtract 3. And now we have negative 3 equals negative 2 square root a half x minus 4. What do I do next? What do I move next? I can't square the square root until it's just a square root. So what do I move next? Three over 2 equals the square root of a half x minus 4. Then what do I do? You have to square both sides or the radical doesn't go away. When you square, do you get a plus or minus sign? No, it's only when you square root. Crazy people put plus or minus signs when you square. I feel like you just want it to be a positive answer, you know? You just want it to be positive. Okay. That's great. I'm glad you were committed. So a half x minus 4. And then, what do we do? Add 4. And then we're not going to math enter enter. We're going to do real math. We're not going to put in brackets and math enter enter. So we're going to go 9 over 4. And then we have 4 over 1, but we need to be over 4 in order to add it. So this is over 1, so we're going to multiply by 4 and 4. So it's going to be 16 over 4. And you were taught equivalent fractions, which is what we're doing right now, in grade 5. I know, because I'm dealing with some grade 5 kids. They're doing it right now. So you did. You can't be like, no, I didn't. Yeah, you did. You were in this curriculum. You totally did. Yeah, you did. Okay, so maybe you revolted and chose not to, but your teacher taught it to you. Okay, then we add them. So we get 25 over 4 equals 1/2 x, and then multiply by 2. Now, when we multiply by 2, 2 is over what? 1. So we don't apply the 2 to the 25 and to the 4, you crazy people. We only apply it to the top, okay? Because it's over 1. So we get x equals 50 over 4, which can reduce to 25 over 2. So my x-intercept is 25 over 2 and 0. Okay, we're going to flip over. Radical graphs, I believe, are the easiest thing to make equations for, as long as you pay attention so I don't lose you. Okay. Radical graphs are really easy to come up with transformations, which other graphs are not. Other graphs, you have to find the stretches and the reflections first, apply them, and then move it to see how far away the transformations were. But radical graphs, you can get transformations instantly. The horizontal translations, instantly. How? Vertical translation, instantly. Yeah. By the original point, because the original point is normally on the parent function, which is y equals square root x, the function that hasn't been moved, is at what? 0, 0. Is it at 0, 0? No. If it's not at 0, 0, you have horizontal and vertical translations, because that's the only thing that can move that point. Remember, because other than that, stretches and reflections don't move that point. You're multiplying by 0. It does nothing. So where did it move? 1, 2, 3, left. 1, 2, 3, 4, up. So I can do my translations right off the bat. We're going to have y equals x plus 3 plus 4. The next thing is also easy, the reflections. If your graph has not been transformed, remember your original graph, the y equals square root x graph? It's here and up to the right. We agree? So if your graph is not up to the right, it's been reflected. Is this graph up to the right? No, it's down to the right. So where did it flip? Across the x-axis, which means it affects the y. Now, I'm going to go back to the previous page. You do not need to. You just follow along, okay? Don't go there. Just follow what I'm saying. So on your original parent function, the y equals square root x graph, look here. The 2 points which are side by side make a 1 by 1 box. We agree? A perfect 1 by 1 box. So if between your first 2 points you make a perfect 1 by 1 box, it has not been stretched at all. Okay? So let's go back here. Between these 2 points, what am I making? Perfect 1 by 1 box. So I'm done. That's my equation. It is done. There are no stretches. Okay? Let's look at the next one. How do we get the translations on the next one? Wow, he needs to turn down his whatever's going on over there. So, how do we get the translations? I feel like I have to scream over the TV in the next room. And TV. Silly me. Smart board. TV thing. So what do we do? You count how far away it moved from 0, 0. 1, 2, 3, 4, 5 left. 1, 2, 3 down. Remember, once you have your equation, you could type them into your calculator and see if they actually match it. That's the great thing about them. So we're going to get y equals square root x plus 5. I didn't leave space. Start. Minus 3. We agree? Is it up and to the right? Is it up and to the right? Yes. So are there any reflections? No. Is it a perfect 1-by-1 box? Keep in mind that the rectangle that we make out of this has to be a 1-by-something box. If it's a 1-by-1, there's no stretches. If not, it has to be a 1-by-1 box. So the best way to make a 1-by-1 box here between the points is to make the 1 be a vertical one. It's a rectangle, correct? To go from one point to the next. My vertical is 1 still, so is there a vertical stretch? No. My horizontal is now 4. So I have a horizontal stretch by a factor of 4. When I put that into my equation, it's a fourth. Now, we can also figure out the vertical stretch from here. Anything under a radical you can take out by doing what to it? If I have square root of 4, I can square root it and it's a 2 and it can come out, correct? So if I want to take this quarter out and have a vertical stretch instead, I can say or y equals, when I take a quarter out, I'm just rooting both numbers, correct? So what's the square root of 1? 1. Good job. What's the square root of 4? 2. So it's a half. That's it. So I can either say that this thing is stretched by a 4, by the horizontal, or vertical by a half. And I'm going to show you why the vertical by a half actually works. Because I didn't have to go up 1 and over and make a box this way, right? Instead of going up 1 and over, what I could have done is I could have went over 1 and up to where I hit it, and then over. Then look, now I would have a horizontal stretch of 1, and my vertical stretch would be, how far up did I go to get to this? A half. Is that one easier to do though? No, I would always do the one that makes you a nice rectangle with 1 as one of the heights, and then just change the other one by squaring it to put it under the radical or square rooting it to take it out. So let's look at this one. So this one has been moved 1, 2, 3, 4, 5 to the right, or 1 down. And by or, I mean and 1 down. I said or. So I'm going to get y equals x minus 5. I need to leave a space. Why do I keep not leaving a space? Minus 1. Then we check our reflections. Is it up and to the right? No. It's actually up and to the left. So it's to the left that changed. In order for it to be to the left, what I reflected? The y-axis, which means I have a negative x. We agree? Then I do the box drawing. Is it better to have a vertical rectangle in this case or a horizontal rectangle? Vertical. So horizontally, I'm still 1. Vertically, I'm now 2. So what kind of stretch? Vertical stretch by a factor of 2. Or I could put it inside the radical. How could I put it back under the radical? Square it. To take it out of the radical, you square root it, because it's under the square root sign. To put it into the radical, you square it. So we're going to get y equals square root negative 4 x minus 5 minus 1. Now people will say it didn't move, didn't stretch horizontally by 4. That's not horizontally by 4. That's horizontally by 1/4. So if I only went up 1 and then over, what kind of little box did I make? A 1 by 1/4 box. That's way harder to do, correct? It's way easier to do the other one and then just put it underneath or take it back out. You try D, and then 3A and B. Try them out. So this one we moved 1, 2, 3, 4 to the right. 1, 2, 3, 4, 5 up. So we're going to get y equals square root x minus 4 plus 5. And it is not only is it not up and to the right, it's down and to the left. So that's like the best case scenario, because then you know there's both negatives and you don't have to remember which one's which. Now, best case scenario 2 is every single time none of these have f's in them, correct? We could type them into our calculator and see if they match. If it's reflecting the wrong way, you put it on the wrong one. At least, the very least, you should catch yourself. Okay? Now, I'm going to make a box. It's going to be a vertical box. Horizontal 1, vertical 4. So I can put a 4 here. Or I can take it and put it inside, and what would it be? 16, which is a horizontal stretch by a factor of 1/16. That's why it's so super tiny inside. Now these ones, the domain and range, vertical stretches do not affect your domain and range. What affects your domain and range? Your translations, because they'll move that initial spot, right? And reflections can cause it, instead of it being up and to the right, it could be down and to the left, which would make it inequalities changing. Okay? So this one is at 5. So I know that I for sure have a horizontal translation of x minus 5 and a vertical up 2. Right? Now, this one is greater than 5. So there's no reflection in the y, correct? It's still to the right. But this one is less than 2, so it's actually down. So if it's down, I have a negative here. This one, I have y equals x plus 2. I have no idea what's going on. And then minus 4. It's really loud. It's really loud next door. Maybe. This one here, we have less than negative 2. So instead of our x being to the right, it's actually now to the left. So I have a reflection in the y, which means I have a negative x. And this is still greater, so that's it. Okay? This is your homework. Just this portion. Yeah. No. People do homework and I do homework checks. Shouldn't be the case when you're 18. You should just do them on your own. You're going to be. You're released into the real world and paying for your education next year. You might as well start doing it now when you don't have to pay.